Welcome to qnawire.
Hi there. 2.8 number 64 may look pretty intimidating at first, so let's solve it here together. We're dealing with a piecewise function f, defined like this in 3 separate pieces, and it's going to be very important as we solve this problem to pay close attention to which of these 3 pieces our inputs are in. So let's keep referring back often to this definition of our function f. It'll be very important. For now, though, let's start with part A, which asks us to find kind of a funny looking symbol, which we've probably never seen before in our lives because it's just been defined in this problem. It's the left-hand derivative of the function f at the x value 4, and the only thing we can do is use the definition that they just gave us, so that's what we will do. We're just going to copy the definition they just told us in this problem, limit as h approaches 0 from the left, of, big fraction, f of, now you notice that the a value in our case is 4, so we can simply substitute the number 4 anytime we see the variable a in their definition. So let's do that. We write 4 plus h minus f of, once again, instead of a, we will write 4 all over h. Now, here's where it's very important to notice as h approaches 0 from the left. Now this means that h is going to be less than 0. This is important because looking at our input here, 4 plus h, we need to figure out, in order to write out what f will be, we need to figure out which part of the domain 4 plus h is in, which of these 3 pieces. So let's look. If h is less than 0, this means 4 plus h is less than 4. Make sure you're convinced of that before we move on. And therefore, since our input, right here, is less than 4, well, let's look. That puts us in this second piece of the domain. Right, if our input is less than 4, that means the function is defined as 5 minus the input. So let's go back and we will use that as we continue. So this part's still the same. We just said f of 4 plus h is really 5 minus the input. And the input is 4 plus h. Now we have to be careful again. F of 4, to figure out what that is, once again, let's look back at the function. We want f of 4, and we can look, well, 4 is certainly in this part of the domain, since 4 is greater than or equal to 4. Therefore, we'll use that part of the definition with the input 4, which is 1 over 1, which is 1. So f of 4 is 1. Let's remember that. And we write 1 instead of f of 4. Okay, this looks not too bad now. We will keep this part. 5 minus 4 minus h minus 1. Just a little arithmetic on top will give us 5 minus 4 is 1, minus 1 is 0. We're left just with this. And as h approaches 0 from either direction, certainly from the left, this should be a pretty familiar limit. We're going to get negative 1. And that's the answer for the first part of part A. The left-hand derivative of f at 4 is minus 1. Okay, we're halfway through part A. Now to get the right-hand derivative, we simply do the exact same thing using their definition, and only one small thing will change. So let's take the right-hand derivative of f at 4. The only thing that changes, if we look at their definition, is that h will now approach 0 from the right. Everything else is the same. So once again, f of 4 plus h minus f of 4 all over h. Once again, it's important that h is approaching 0 from the right. This means h will be greater than 0, and that means 4 plus h will be greater than 4. So looking back at our function f, if our input is greater than 4, well, that means we're in this part of the domain. So our definition is f of some input is 1 over 5 minus that input. Let's remember that as we carry on. So we just said f of our input, it's 1 over 5 minus that input, and our input was 4 plus h, minus f of 4. We can remember from last time, f of 4 is just the number 1. That hasn't changed. All over h. And now, just a little cleanup. As often with calculus problems, there's a little bit of calculus and a lot of algebra. So just make sure that we don't make any mistakes here in computing these little fractions. 5 minus 4 is 1 minus h there. We are going to need to combine these two fractions on top in order to simplify, so let's do that now. Let's rewrite 1 as 1 minus h over 1 minus h. This way the two denominators are the same, and we'll be able to combine them next step. So we're almost there. Now that the denominators are the same, right, we know that the denominators will be 1 minus h. Subtracting across the top, 1 minus 1, and this would be plus h. Be careful, that's a common mistake. We're subtracting all of this, so it's minus 1 minus h, gives us a plus h. All right, nearly there. 1 minus 1 plus h gives us just h on top. 1 minus h over h. And coming to the end here, we can rewrite these in many ways. Perhaps easiest to see if we just rewrite like this. And once again, since h is never equal to 0, we're simply approaching 0. Those h's will cancel. And hopefully we can see that we are left with limit as h approaches 0 from the right, 1 over 1 minus h, which is 1. And we have finished part A. That is our right-hand derivative at 4. It's just 1. Part B asks us to graph the function f. So to graph it, let's just look back at how f is defined. Let's first graph this first section. So whenever x is less than or equal to 0, the function is simply 0. So that should be not too bad. So anytime x is less than or equal to 0, so right in this part of the graph, our function is simply 0. We know how to graph that. It's simply a straight line with a height of 0. Anytime we are less than or equal to 0. Good. The next part, when x is between 0 and 4, our function is 5 minus x. So we just said between 0 and 4, that's this part right here, 5 minus x. Well, that's just a straight line with a slope -1 and a y-intercept 5. So we know how to sketch that, and we stop once we hit x equals 4. And so open circles on either end there. And that takes us to our last, over here, our last part of the definition. When x is greater than or equal to 4, 1 over 5 minus x. Okay, so when x is greater than or equal to 4, we'll make that blue. So this whole part of the graph, 1 over 5 minus x. And we hopefully recognize that as, well, we can see there's an asymptote at positive 5. So we can sketch that in with the dotted line as you usually see them. And we'll assume you're somewhat familiar with this graph here. We can tell as x approaches 5 from the left, we're going to have a limit of positive infinity. So it will go up forever as we approach 5 from the left. To figure exactly the height at 4, let's just plug in 4 for x. 5 minus 4 is 1. And we already knew from doing the problem, f of 4 equals 1. Don't forget, f of 4 equals 1. So there we go, f of 4 equals 1. Let's just connect these as nicely as possible. And then on the other side, something along these lines here. You notice that as we approach 5 from the right, at 1 over 5 minus x, we'll have negative infinity. And these were all graphs that we're familiar with from earlier in the text. So there's our graph, and that completes part B. Parts C and D, well, let's use our graph to answer them. We might as well use our hard work. Where is f discontinuous, we're asked in part C? Well, we can simply look, and it shouldn't be too hard. We can tell discontinuous, the only places, certainly at x equals 0, we have a jump discontinuity. You can see right here from the left, we're going toward a height of 0, and from the right toward a height of 5, so x equals 0. 4 is okay. We do have a continuous, or f is continuous at x equals 4 from the left and from the right. We're approaching the same height, which is also f of 4. And the vertical asymptote then is the only other discontinuity, so x equals 5. And those are the two x values at which our function is discontinuous. Those are the only ones. And finally, part D. Where is f not differentiable? Well, we can see most of the graph certainly is differentiable. When x equals 0, less than or equal to 0, our function is simply f of x equals 0. That is differentiable. It has a derivative of 0 everywhere here. Certainly, since you cannot be differentiable, a function is not differentiable if it's not even continuous, x equals 0 must be a place in the domain where the function is not differentiable. This entire part here between 0 and 4 is differentiable. We can even see the derivative is -1. At 4, well, remember they told us that f prime of 4, the derivative, exists only if the left and right hand derivatives equal each other. Let's just look at our work from part A. The left-hand derivative at 4 was -1. The right-hand derivative at 4 was +1. They're not the same, so clearly f prime of 4 must not exist. We can see that just by looking here as well. The function comes to a point, a cusp. So there's no derivative at 4. And likewise, x equals 5, not even continuous there, so it cannot be differentiable. Those are the only 3 places where our function is not differentiable. So a bit of a whirlwind there. I know there were a lot of steps, but hopefully this made sense and hopefully this was helpful.